Welcome to this iChemist Safety Center webinar on how to learn more from accidents. I hope everybody can hear me. My name is Dr. Susanna Gyenes, Deputy to the Director of the iChemist Safety Center. This webinar will describe a systems approach to accident prevention. The topics covered will include why are we not learning enough from accidents today? Do operators really cause most accidents? And how we can increase learning. Examples from the process industry will be used to describe a new, more effective approach to analyzing the cause of accidents. The new approach is starting to be adopted widely for aviation accidents and incidents. As we progress through the webinar, you will be able to type your questions or make your comments in the question box on the right-hand side of your screen. We will endeavor to answer your questions at the conclusion of the presentation, as well as by email after the session. Today's webinar presenter is Professor Nancy Leveson. Nancy is Professor of Aeronautics and Astronautics at MIT. She has published over 200 research papers, and she is author of 2 books, Safeware, System Safety and Computers, published by Addison Wesley, and recently translated into Japanese, and Engineering a Safer World, published by MIT Press, and currently being translated into Japanese and Chinese. She consults extensively in many
Oh, I'm clicking.
I hope that everybody can see now the screen.
Okay, can you see my screen?
Yes?
No one sees your screen, it says. Oh, I got it. I think they can see it now. Can you see it now?
Yes.
Oh, good. Okay. So let me get this. Why won't this? Here we go. Good afternoon or morning, depending on where you are. It was about 10 years ago I visited an oil refinery, and they told me they had thousands of accidents or incidents, especially incidents a year. And they asked me how could they decide which ones they should investigate. And my response was that if they were asking the wrong question. If they investigated just a few more thoroughly, they might not have thousands of incidents. So that's what I'm going to talk about today, is how to learn more from accidents. I've been involved in the official investigation of many major accidents. These are just a few of them here. And I've looked at several hundred more. There's lots of common factors. Accidents can be avoided, but it's going to require doing things differently than they are today, and learning more about the accidents that we do have. So the first question I want to answer is, why aren't we learning enough from accidents? And there are certain common problems in accident analysis. Root cause deduction, oversimplification of causes, hindsight bias, a focus on blame, and a narrow view of human error. And I'm going to say a little more about each of these. Let's start with root cause deduction. A colleague of mine at MIT came up with that term, and I like it. Root cause deduction means that we're really seduced by the idea of there being a root cause. So we assumed what there is because it gives us an illusion of control. If there's only one root cause, then we just get rid of that, and then everything's fine. Usually we focus on operating error or technical failures, ignoring the systemic and management factors. But what this does is lead to a sophisticated game of what's called whack-a-mole. In other words, what we do is fix symptoms, but not the process that led to those symptoms. And we end up in continual firefighting mode, having hundreds of accidents and incidents over and over again, and the same accident really continually. Related to this is an oversimplification of causes. Almost always there's operator error, flawed management decision-making, flaws in the physical design of the equipment, safety culture problems, regulatory deficiencies, and so on. And unless we understand and don't oversimplify the causes and understand the role of each of these things, we're not going to be able to learn enough. Unfortunately, we want simple answers to what are really complex systems. So here's an example, find X, here it is. So what happens when we do this is we get simple and usually useless answers. So many of our problems in learning stem from the accident models we use. And the model that everyone basically uses today is the domino model. An accident model identifies how we learn from and how we try and prevent accidents. It's the way we explain why accidents occur. And the model, again, that we use today is a linear chain of failure events, where we have event 1 and that causes event 2, which leads to event 3 and leads to event 4, and then finally event 5 with the explosion or whatever happens at the end. And this was actually a really old model. The domino model is from 1932, but it goes back 100 years in terms of explaining causality. It's a couple hundred years. You may have seen the Reason Swiss cheese model. It's the same thing. It's just a substituted Swiss cheese for dominoes. We still have these events. Each of them is a failure of some kind. At the end, we have an unsafe act, which leads to a mishap or accident. It's interesting, the act is usually considered by a human. Now, the man who had created this Reason was a psychologist, and it's not surprising. But if we only look at human behavior in each of these acts, and that's what the focus is on, you forget all the other things. And so, for example, the wings could fall off the plane, and we'd still have to blame the pilot. So let me show you an example of an accident. This is an old accident. It happened in Europe, in the Netherlands, I believe, or Belgium. And it was a ferry that sunk called the Herald of Free Enterprise. It was, and several hundred people died. It was a terrible accident. And basically, if you look at the events, the assistant boatswain was responsible for closing the loading doors. The first officer was supposed to check that the doors were actually closed. But to keep on schedule, the first officer returned to the wheelhouse before the ship dropped its mooring. And that was actually common practice. He was basically left the closing of the doors to the assistant boatswain. But the assistant boatswain had taken a short break after cleaning the car deck upon arrival at Zeebrugge, which is where this happened. He returned to his cabin, and he was still asleep when the ship left the dock. So nobody closed the doors. The captain assumed that the doors had been closed because he couldn't see them from the wheelhouse due to their construction, and there were no indicator lights in the wheelhouse to show the door position. And if we look at this accident, we're going to find one or all of these people responsible for it. But Jens Rasmussen, just give credit for this diagram, show what we need to understand the interactions among causal factors. So at the top of this diagram, we have capsizing. At the very bottom, we have all kinds of things that contributed to this accident: the vessel design, cargo management, passenger management, harbor design, vessel operation, traffic scheduling, and all of these things interacted. So the vessel design on the left there, the three: vessel design, cargo management, and passenger management, all interacted to cause an impaired stability of this thing. The reason it sank and capsized is because it wasn't as stable as people assumed it was. And all of these things interact. And unless we understand the interaction of the causal factors, we don't just look at them as single individual component failures, we're not going to be able to understand the accidents. So the limitations of the chain of events model is it assumes independence of all the events. We end up blaming the human operator or physical failure in the chain. We can't handle complex human behavior, software, systemic factors, design flaws in complex systems, organizational social factors, culture, accidents involving non-failures, and these interactions among the causal factors. So we end up not understanding much about how the accident, why it occurred. A second problem is something called hindsight bias. Before an accident is really clear, I mean, it's not clear, I'm sorry, before the mishap on the left, there's all these things happening all at once in different order, information's coming in, and it's not at all clear what happened. But after the mishap, and we've got the causal connections all in our mind, it's very easy to see what happened. And you'll see this all the time in accident reports. If the operator should have, if they could have, if they would have only, then the accident wouldn't have happened. And the problem is that before the accident and before the events happen, it isn't all clear about this. So there's some examples at the bottom. This is from a accident report of an aircraft that flew into a mountain while approaching Cali, Colombia. And at the end, the causal factor, they said the cause was a failure of the flight crew to discontinue the approach into Cali, despite numerous cues alerting them of the inadvisability of continuing the approach. The problem is that those cues were only clear after the fact. So the investigators said, well, it was clear. They should have known not to do that. But before the fact, they weren't at all clear. Another example is from another refinery accident. I looked at the board operator should have noticed the rising fluid levels in the tank. And it turns out there was no way they could have known that the fluid was rising. All of the sensors were broken and had never been fixed. The high level trip didn't work. There was another alarm in another part of the plant that went off at the same time. There's just no reason that they would have actually noticed this. But after the fact, it's easy to assign this kind of blame. So after an incident, it's easy to see where people went wrong. It's easy to judge about missing a piece of information that turned out to be critical, but only as critical in hindsight after the fact. It's almost impossible to go back and understand how the world looked to somebody not having knowledge of the outcome. So in order to learn, we need to identify why it made sense for people to do what they did. And the real issue is that we need to get away from blame. Blame is the enemy of safety. The goal of the courts and the legal system is to establish blame. When you do consider blame and try to assign blame, people stop reporting errors. Information's hitting, everybody points at everyone else. Don't look at me, it's his responsibility. It was on fire when I got here, and learning is inhibited. But the goal of engineering is not to figure out liability. The goal of engineers is to understand why accidents occur in order to prevent them. Now, I understand there are all kinds of legal issues and other things that tie the hand of accident investigators, but if we can get away from blame, then we can learn an astounding amount more about accidents than we do today. So here's an example. This is from an old accident report, and this was at the end, the conclusions of the report, and it said the National Transportation Safety Board determined the probable cause of this accident was the flight crew's failure to use engine anti-icing during ground operations and takeoff. The flight crew's decision to take off with snow and ice on the airfoil surfaces of the aircraft, and the captain's failure to reject the takeoff during the early stage when his attention was called to anomalous instrument readings. And then they specified, well, why. The contributing factors, they said, was the prolonged ground delay between de-icing and receipt of air traffic control clearance, during which the airplane was exposed to continual precipitation, the known inherent pitch-up characteristics of the B-737 aircraft when the leading edge is contaminated with even small amounts of snow or ice, and the limited experience of the flight crew in jet transport winter operations. Now, what I want you to do is look at this, and if you were concluding who and what would you conclude is the cause and the major root cause, the major factors involved in this accident. Now, unfortunately, we can't speak to each other, but I have a feeling you probably said it was a flight crew problem. Now, and in fact, there's all kinds of clues here. First of all, the flight crew is the only one mentioned in the who. They look at who, and so you're going to end up with the flight crew. And there's this word failure, the flight crew's failure to use, the flight captain's failure to take off. So if we look at this, the problem is that first of all, we only looked at who, and the use of the word failure is a pejorative word. It's a judgment. It's used to assign blame. If you say the captain's failure to reject the takeoff during the early stage when his attention was called to anomalous engine instrument readings, then it's pretty much clear you're saying the captain was at fault. What if we stated the same thing, but without the word failure? The captain did not reject the takeoff during early stage when his attention was called to anomalous engine instrument readings. If we look at it that way, we immediately reach the conclusion that we have to know more. We need to know why the captain didn't reject the takeoff. The first one, it doesn't really lead us to that because it's already concluded. It was the failure to reject takeoff, and that was the cause. And so I call this the accusatory approach to accident analysis, where we focus on who to blame. Now let's look at the same accident written differently. And instead of looking at who, we look at what. So we say and again, this is the same icing accident, the icing on the wings. What? Based on the available evidence, the accident board concludes that a thrust deficiency in both engines, in combination with contaminated wings, critically reduced the aircraft's takeoff performance, resulting in a collision with obstacles in the flight path shortly after liftoff. So instead of looking at who, we look at what. And then we try and understand why that happened. The reason for the thrust deficiency, maybe engine anti-icing was not used during takeoff and was not required to be used based on the criteria for wet snow in the aircraft's operation manual. The engine inlet probes became clogged with ice, resulting in false high thrust readings. One crew member became aware of anomalies and cockpit indications, but did not associate these with engine inlet probe icing. And despite previous incidents involving the same kinds of false thrust readings during winter operations, the regulator in the industry had not effectively addressed the consequences of blocked engine probes. Now, when you read this, I hope you're going to get a totally different view of what happened in this accident. Instead of blaming everything on the pilots and focusing on what the pilots did wrong, this looks at what happened in the whole system and why the events occurred, not who was responsible for them. So you get a very different view of the accident. And as I say here, do you now think it was just flight crew failures? Are there other factors? And if you can look back at this later, this is going to be posted. And again, but the difference is on the left was the first accusatory who, why explanation. And the second is an explanatory what happened and why. And instead of assigning blame to a human or to an operator, instead we try and understand just what happened. And I ask a question, do you think the recommendations will be different? And again, when you go back and look at this, you'll see the recommendations are going to be totally different given how we describe the accident and the loss. Let me also make a few comments about operators. You know, we've all heard, this has been said over and over again, 80 to 90% of accidents are caused by operators. Is that really true? Well, in the traditional view of operator error, the assumption starts from that the operator error is the cause of most incidents and accidents. And you saw in that last accident, the example that I gave, they immediately focused on what the pilots did wrong. So what do? Well, if it's operator error, you should do something about the operator involved. Fire them, retrain them, whatever. Or do something about operators in general. Marginalize them by putting in more automation, rigidify their work by creating more rules and procedures. Here's one of my favorite cartoonists. Fumbling for his recline button, Ted unwittingly instigates a disaster. Our behavior, human behavior, is always impacted by the context in which it occurs. And we don't think we're being impacted. We think that we have free will, but we don't. We are affected greatly by the context in which we happen to find ourselves. So the new systems view of operator error, and this is the one that I like and use, is that human error is a symptom, it's never a cause. It's a symptom of the problems in the system and design. And all behavior, as I said, is affected by the context or system in which it occurs. What we're finding in the systems we're building today, the role of operators is changing. Because of the tremendous use of computers and software, they're supervising rather than directly controlling systems. And the systems are so complex, even the designers don't understand them, and certainly the operators don't. And you find all the time on aircraft, they've done recordings in the cockpit, and pilots will be saying things like, what's it doing? Why is it doing that? What's it going to do next? They're really confused by the automation. And we're basically designing systems in which operator error is inevitable. And then we blame the accidents on the operators rather than on the designers. So to do something about human error, we have to, instead of just blame them and then stop there and fire them, or if they're not already dead, we have to look at the system in which people work. There are various things I mentioned: design equipment, usefulness of procedures, but there's lots of things. The bottom line is that red statement there. Human error is a symptom of a system that needs to be redesigned. Here's another example from that Cali, Colombia accident where they flew into a mountain. And again, this was one of the probable causes. There were 4 causes, all of them attributed to the pilots and the flight crew. And again, using the word failure, as you see, failure of the flight crew to revert to basic radio navigation at the time when the computer-assisted navigation became confusing and demanded an excessive workload in a critical phase of flight. So it was the pilot, the flight crew's responsibility not to be confused. So it was their fault that they were confused by confusing automation instead of the designers who designed the confusing automation. This is not going to help us get very far in improving systems. So how can we increase learning from accidents or incidents? Well, so our goals are for an accident or incident analysis then should follow from some of the things I've been saying. We want to minimize hindsight bias. We want to provide a framework or a process to assist in understanding the entire accident process and identify the systemic factors, not just what the operators did wrong. We need to get away from blame, who, and shift the focus instead to why and how to prevent the same events in the future. In other words, we need to determine why people behave the way they did, not just focus on what they did wrong, and the weaknesses in the safety control structure and the controls, and I'll explain what that is in a second, that allowed the loss to occur. So I'm going to talk briefly. I'm using here an analysis method that we created based on these principles, but there could be others. I'm not trying to sell one analysis method, but CAST stands for Causal Analysis Using System Theory, and it provides an example of how to do this kind of thing. CAST is a structured technique to analyze accident causality from a system perspective. And what it does is help to generate the questions that need to be asked, because we aren't asking the wrong questions. We're stopping with operator or pilot or whatever failed. It's a paradigm change from what's done by other tools today. Instead of looking and focusing on the event chain, we focus on such questions like, why didn't the design controls prevent the accident? We always design controls and protection into systems. And as we have accidents, we add more controls. So we need to understand, why didn't those controls work? And what changes are needed to prevent future accidents? What changes in the system and the controls, not what changes in humans, or just what changes in humans. And what we do is identify how each of the components in the control structure of the system contributed to the loss. The approach is a what, why, or explanatory approach, using the terminology I introduced previously, not a who, why, or accusatory approach. Now, I'm going to give you a little bit, there's just not time to go through a whole example, but I'm going to give you a little bit of an example of CAST analysis of the shell explosion in a chemical factory, chemical plant in the Netherlands, owned by Shell, and it was in a place called Moerdijk. So it's called the Shell Moerdijk analysis, and there's a link there that you can go and look at the whole thing. There's also other examples and information at the other link, and I'll also show you a book with lots of examples in it later. So CAST is based on something called STAMP. STAMP is a new model of accident causality I came up with about 20 years ago. And instead of thinking of accidents as chains of events, which is what we've been doing again for 200 years, accidents are instead conceived as being caused by complex interactions among humans, hardware, software, and social structure. It's not just the failure of humans or the failure of hardware or whatever. It's caused by the interactions between all these things. And it's a change of focus. It's really a paradigm change. Instead of looking at examined failures, which is what virtually everyone does now, or examine event chains, and we instead focus on determining why the design controls were ineffective. And I'm going to show you an example from this Shell Moerdijk accident. But I want to stop first show you, there's one thing you have to understand. It's pretty simple. The control structure is also often called the safety management system, and you're probably more used to calling it a safety management system. In engineering, it's really a series of control loops. And if you see here, there's a controller and a controlled process underneath. The controller has certain responsibilities that they have with respect to safety. They also have a process model. What does that mean? Well, if it's human, it's a mental model, which may mean more sense to you. But software also has a model of the process. What it is a model of the state of the thing that's being controlled, the controlled process at any time. The controller uses this state assumptions about what the state of the process is to issue control actions on the controlled process, and then gets feedback about the actual state to update the process model. Lots of accidents are explained by the controller's process model being inconsistent with the model of the actual controlled process. For those of you who have engineering backgrounds, this is going to look like a feedback control loop, which is exactly what it is. As I said, when accidents occur, it's often because the operator thinks that the system was in a certain state, and it turns out it isn't, and they do the wrong thing. That's a much better model of causality than simply the controller failed, whatever that means. So the operator thinks that the level of the fluid in the ISON tower is not increasing, and then doesn't do anything about it. And it turns out that it was increasing because they didn't get adequate feedback. All right, so let's get to Shell Moerdijk. So here's how we can put all those feedback control loops together. This is a simple model of the safety management system, or the safety control system for this plant. The part in brown is the actual chemical plant itself. At the bottom is the chemical process. Then there's a process control system that's controlling the chemical process. There are operators that are operating and using the process control system to control the chemical process. There's also a link, as you see, from the operators directly to the chemical process, because the operators have some things they can do directly affect the state of the chemicals. There's a safety management group. There's plant operations, which is controlling all of this. Up on the upper left, you can see Shell Global. This is the global parts of Shell management. And in there, we have three things. Shell Projects and Technology is their design process, their design group that helps design the actual plants. We have Safety Management, which is supposedly managing safety over the whole, all of the plants and all of Shell. And then we have Executive Management over that. Over on the right, we see the Netherlands government and various kinds of oversight agencies have some type of control over the plant operations, and the EU above that. And then in purple, light purple, the emergency management. There's state and local emergency management, which has control over public health and is supposed to be prepared in case and to respond when an accident occurs. Now, I didn't put in all the control actions and the other things just to make this less, I didn't label them, make this less messy, but I do have them in the actual example that you can look at. So what do you do first? Well, we first establish the fundamentals for analyzing the accident, the explosion. There was a fire and explosion in the plant. So the hazard is, there are two hazards I identified here: the exposure of the public or workers to toxic chemicals, and there are constraints that need to be enforced. Workers and the public must not be exposed to potentially harmful chemicals. Measures must be taken to reduce exposure if it occurs, and means must be available, effective, and used to treat individuals inside or outside the plant. Sorry, I will stutter there. And all of those safety constraints must be enforced in the safety control structure, the safety management system, the thing I just showed you here. This whole process, this whole control structure has to enforce the safety constraints, and if they don't, then an accident can occur. There's another hazard: explosion or uncontrolled release of energy and or fire. And again, there's more safety constraints. Chemicals must be under positive control at all times. Runaway reactions must be prevented. Warning and other measures must be available to truck workers in the plant, minimize losses in case they aren't under control unless there is a runaway reaction. And means must be available, effective, and used to respond to explosions or fires inside or outside the plant. And each of these safety constraints would be assigned to components in our control structure. Again, assigned to here, obviously, the state and local emergency management is responsible for protecting public health in case there is an accident. But all of these components are assigned specific kinds of responsibilities. So the next step is most people then start looking at the events. But looking at the events isn't enough. We need to look at why the events occurred. Identifying the events, which most people focus on, provides almost no useful information. So I've got a couple examples here of what happened during this accident event. On the first one, an automatic protection system was triggered that was designed to prevent liquid from entering the exhaust gas system, the flare, but preventing the liquids from entering the flare also prevented the gases in the system from being discharged, increasing pressure in the reactor. And this was identified in the accident report. But this raises all kinds of questions, like, did the operators notice this? Was it even detectable by them? Why didn't they respond when this occurred? This seems like a predictable design flaw. There's a safe interaction between two requirements: unsafe interaction, preventing liquid from entering the flare, and the need to discharge gases to the flare. Why was that identified in the design or hazard analysis efforts? If so, why wasn't it handled in that design or in operational procedures? If it wasn't identified, why wasn't it? And those are the things we need to find out, the questions we need to answer in order to generate recommendations that will be effective in preventing this in the future again. Or not just this, but all kinds of accidents that really have the same cause. Here's just another example. Continued warming up of the reactors caused more chemical reactions to occur between the ethylbenzene and the catalyst pellets, causing more gas formation and increasing pressure in the reactor. And that generates, again, to understand that's just not useful. To understand and generate good why the thing occurred and better recommendations, we need to answer these kinds of questions. Why wasn't the increasing pressure detected and handled? If there were alerts, why did they not result in effective action to handle the increasing pressure? If there were automatic overpressurization control devices, which there were, for example, relief valves, why weren't they effective? If there weren't automatic devices, then why not? Was it infeasible to provide them? So by using the process, and I'm not explaining the detailed process of CAST, but by using CAST, what we can do is generate the questions that we need to ask in order to really identify all of the factors involved in this accident. Some of them I found in the accident report. The accident report was very thorough, very long. I could answer some of the questions from it, but a lot of them were never asked, and the information was never identified as important to find. When you get the information, answer the questions, what the analysis in CAST has a certain format. For each component, we identify the responsibilities. What were, for example, the responsibilities of the process control system? What were the responsibilities of the regulators? What were the responsibilities of the operators? What were the responsibilities of management? The unsafe control actions that occurred, the contextual reasons for the behavior, why did it occur, and also the mental model flaws or process model flaws that contributed to those unsafe control. For the control structure as a whole, then, we do that for each of the individual components. For the control structure as a whole, we also have to look at flaws in coordination and communication among components. Why did these different components that should have cooperated and communicated, why didn't that solve the problems? Were there flaws in the communication? What was the role of the industrial and organizational safety culture in this? And I'm going to show you some examples. I'll talk about safety culture here in this plant. What about the safety information system? Safety information system is one of the most important factors in preventing accidents. And why didn't it do it in this case? And various dynamics and changes over time. Systems are never static. They're continually changing. So what kinds of changes, how did this thing migrate to a state of higher risk, which is what we see in almost every accident? There are changes that occur both within the system and in the environment of the system that often end up leading to accidents. And we have some new tools and other things to identify this migration towards states of higher risk. After this, I'm joining a teleconference call with some airlines that are trying to use this to identify when they start seeing lots of precursors, when they start seeing leading indicators, and how can they identify those. So in the end, and this is just in the end, there were, in the whole analysis, and if you look at the CAST analysis, it's long, and I just don't have time to go through it all here, and I don't have time teach you how to do this, really. But what we found was that, and almost always find, is that there are inadequacies found throughout the whole safety management system. Every single component didn't respond appropriately in the way that people thought in order to prevent this, what they would to prevent this accident. So what we need to do is look at what didn't they do that they should have done, and how can we, and not to blame them, but to figure out recommendations of how we can strengthen the entire safety control structure. Maybe we move responsibilities around. Maybe we need better feedback. There's all kinds of reasons why the controls were ineffective, and we need to identify them in order to prove them. So there were problems in the physical design. There were problems in the process control system. It wasn't designed to help the operators. This accident occurred during after a maintenance stop when they were restarting the reactor. And the process control system wasn't designed to provide any information to the operators during this restart. Well, we know the most hazardous part of some of the operations is during a maintenance stop and a restart. So why they made a decision, and that was never answered in the accident report. So I couldn't answer the question why they would make a decision not to have the process control system help the operators is beyond me. The operators. Now, it's interesting. The operators were blamed, and usually are blamed, for the whole accident. In fact, if the operators in this case probably were inconsequential and were the least involved in responsible for this accident. They acted appropriately, or at least understandably, given the context in which they found themselves, like no information from the process control. So they didn't have the right information. They were given incorrect work instructions, which they followed. If they hadn't followed, of course, they would have been blamed for that. They're going to be blamed either way, but the work instructions were wrong. And they did what they were told to do. And their lack of training and required skill and knowledge in performing the work. In addition, they were provided with almost no assistance from the process control system. As I said, while many of the tasks that they needed to do required intense attention, precision, mental effort, deep understanding of process dynamics, and frequent adjustments to a continually fluctuating process. And they just didn't have any assistance at all in doing what are some of the most difficult parts of their tasks, of their daily tasks during this restart. And the risks were not communicated properly to them. Management relied on the operators to see something strange and stop the process, but they didn't provide the information and training to ensure that it was possible for the operators to do this. So if you look at this, you see probably the operators had the least responsibility for this accident, and we need to change everything else, but not necessarily the operators. But we can find problems in the plant safety management, in operations management, in Shell projects, the Shell design, the Shell corporate safety management, the Shell executive level corporate management, the catalyst manufacturer. The catalyst had changed over time and nobody knew it. And in fact, one of the things that they had assumed in their risk management was they had done a study 30 years before that this catalyst was inert under these conditions. There was zero chance of a runaway reaction with this catalyst. And so everybody assumed that, and they didn't, but over time, the catalyst composition had changed, the manufacturer had changed, and now it was not inert. And you're going to say, well, how could they have known that? Well, they could have done an update on the study, the risk analysis. But worse, it turns out that within Shell, there were two other plants, one in Singapore and one in China, that were very similar to this one and that had the same problem with the catalyst. The catalyst had led to an explosion, and for some reason, nobody seemed to know about this. So it could have been, I don't know why, when they designed the Dutch plant, they should have known it wasn't zero risk, but they assumed it was zero risk. So I don't know why it wasn't in the accident report. I would guess it had something to do with the safety information system or whatever. There were also, as I said, flaws in the interactions among the SMS, the control structure components. Again, they said nothing about the safety information system, but this had happened before. Why didn't somebody do something about it? Why didn't they know about it? Was it in the information system? If it was, maybe it wasn't easily found. Maybe the people didn't check the information system to get more up-to-date information about events that had occurred within Shell itself, and so on. Lots of questions that we need to answer in order to fix things. And if we ask and answer those questions, we can figure out how to change and improve the safety information system or its use. Safety culture problems. Shell thought they had a wonderful culture. I don't agree. I found all kinds of cultural problems in this. Communication and coordination problems. Again, dynamics and changes over time. The composition of the catalyst is one example. So here are my conclusions. We're almost done. The models that we use in accident or incident analysis determines what we look for, how we go about looking for the so-called facts in an accident, and what facts we see as relevant. Using a linear chain of events model promotes looking for something that broke or something that went wrong in the proximal sequence of events prior to the accident. We usually choose some kind of stopping point arbitrarily in this, where something broke or there was supposed as the operator error in hindsight occurred, and we say that's the root cause. Unless we look further, unless we look at why the events occurred, we limit our learning and almost guarantee that future accidents related to the exact same future factors are going to occur. The goal instead should be to learn how to improve the safety controls, the safety control structure, and not to find someone or something to blame. So where can you get more information? Again, we only had a short while, and there isn't much more time. But there's lots of information available. One place is a book that you see, Engineering a Safer World, MIT Press, 2012. If you look on the web, I'm not trying to sell books. If you look on the Google Engineering a Safer World, the first thing that comes up is a free copy that you can download, PDF download from the publisher. They kind of hide it on the page, but look, it's there. And you can get a free copy of this, PDF copy of this on your computer. Another place, we have a workshop that every year, March 25th to 28th this year. Last year, we had 327 people from 32 countries, industry, academia, government. We have tutorials, panels, user experience. Just about every safety critical industry is represented. You can get more information about that, and you can get more information about various papers and examples. I showed you a link earlier to the Shell mower dive example and the other papers. You can get all of this at this link, psas.scripps.mit.edu. And so I'm ready for questions. We don't have a lot of time. So what I agree, Susanna and I talked about was, if you send the questions and submit the questions, what I'll do is answer them in email to everyone. and provide answers to anyone who has any questions. You can write directly to me also. My email address is easy. It's just levison@mit.edu. And if you misspell my name, it'll still get to me because there's a man whose name is similar to mine at MIT, but he's in the creative writing program. So he gets a lot of mail that's directed to me, and anything that looks like accidents or safety, he just immediately sends on to me. And that's it.
Thank you, Nancy. Thank you so much for this really interesting presentation. And I can see no questions so far. Wait a second, maybe. Can you please explain in more detail what you mean in respect to safety information systems? So there is Nancy, there is a question here. If you can explain, please, what do you mean by safety information systems? Right, then please, yes, please just email the question. We will answer. Nancy will give you the answer to that. And before I close this webinar, I would like to give you information about the upcoming webinar event that you might have received the email already. If not, then just flag it to me, send me an email, and then we will send you the link. This is a webinar about what Longford taught me about process safety, and it will be organized on the 26th of February, same time as now, and it will be presented by Mike Connell. And thank you so much for attending to this webinar. I hope you enjoyed it, and goodbye, everyone. Bye-bye.